thank you for everyone that showed up for the seminar today. And I want to take a moment here to give credit to Ken Haga. He's one of our design engineers who produced a lot of the material that I'm going to show today. In fact, a lot more material that I'm going to show today. And we have about 45 slides. That's about 1 a minute. And basically, my goal is just to touch on each subject. If you see something that piques your interest, here's my contact information. I'm going to display this again at the end of the presentation. And I'd really love to hear from you. If you've got specific questions, you can email or call me. And I will show this contact info again here in just a moment. Okay. Probing is certainly never as easy as it looks or as simple as we would wish it were. So I'm going to start with 4 slides here. It's going to be kind of a little quiz. And each slide is a capture of the same waveform using the same scope. The scope is a 1 gigahertz scope, plenty of bandwidth. The waveform frequency is 200 megahertz. And I want you to look or focus on the shape of each of these captures. So here I'm using a simple passive probe. It's a 500 megahertz probe. So one would think I have plenty of bandwidth there. And the waveform looks a bit like a triangular waveform. Okay, here's the same waveform, same scope, a little bit different setup. I'm using the same passive probe, but and that's this probe here. That's a 500 megahertz 10-to-1 passive probe. It has a 10 mega ohm input impedance. And I'm using, instead of this long ground lead, I'm using a shorter ground and a little tip that allows me to shorten or reduce the length of my connections to the test point. And so the waveform looks a little bit different here. This is waveform number 2 of 4. And here's waveform 3. In this case, I'm using an active probe with really excessive bandwidth, probably around 2 gigahertz. And this probe has very, very short connections on the end. And the waveform is pretty strange. Looks a bit like a square wave. And waveform number 4. This one looks quite a bit like a square wave. And what I've done here is a damping resistor, which you're going to learn about today. But otherwise, this is the same 2.5 gigahertz active probe, and then a pair of leads that are actually quite long. And I mentioned that because that will play some role. And I have a damping resistor here. So your job is to decide which one of these waveforms you believe, and maybe you'll see in one of those 4 slides waveforms that you believe you've seen before. So possibly you've faced this issue. Okay, we're going to start with voltage probes, and later we'll talk about current probes. Voltage probes are the most common type of probe. And if I go to the equipment room and check out a scope and I want to connect to a voltage test point, I'm probably just going to pull the passive probes out of the box or out of the bag that the scope came with and just connect them up and not give them much thought. But if I were purchasing or selecting a probe, I'd want to pay attention to the bandwidth of the probe and consider it against the maximum frequency of the device under test. Certainly, I'm going to ask my salesperson, what voltage range probes do they have, and I'll consider against that the maximum voltage that I want to measure, and then some margin for safety or performance with respect to the probe. And then I might not think about input resistance or input capacitance, but I'm hoping my salesperson is going to bring that up, and you'll see that these 2 items are very important. So as an example, a 10-to-1 probe often has 10 mega ohm input resistance. And sometimes we give that some thought. That determines the DC loading effect. Does it make my device under test signal just a little bit smaller? And the answer is yes, it does. In the case of 10 mega ohms, not much. Increasingly important with increasing frequency is input capacitance. So this gets overlooked a lot, but a passive probe might have something on the order of 100 picofarads, which can be a problem at some point. We'll discuss that. an active probe might have 1 picofarad, which actually could still be an issue at some frequency. So anyway, the input capacitance determines the AC loading effect. So if I have a AC waveform there, does it get smaller in amplitude when I probe it? And the answer is that it does. So the issue is how much. So at 1 gigahertz, input capacitance is going to be an issue. At 10 hertz, input capacitance will not be an issue. And that's a pretty grotesque example, but I'll give you better ones here in a moment. When you look at the specs for voltage probes, this gets overlooked a lot. Go back to the specs section of the manual and look for derating. This is true for current probes too. So that means with increasing frequency, my probe is actually less capable. And I need to consider, will that still make my measurement that I want to perform successfully for me? Okay. So we're going to start with talking about passive probes, and then we're going to move to some a little bit more esoteric probes that are also still passive, and then we're going to talk about active probes. In the passive probe world, and these are pretty low cost, we have 1-to-1 passive probe. That's generally good to about 10 megahertz, or DC measurements. 10-to-1 passive probe is around 10 mega ohm input impedance. General purpose, it has a higher input impedance. This is actually more common than the 1-to-1. And then if I want to measure high voltage, I need higher attenuation ratios, as high as 1,000 to 1. And then we're going to discuss a probe called a Z0 or transmission line probe, and I'll give you a schematic of each of these probes too, so you understand how they work. And then we'll discuss active probes. Active probes come in 2 flavors: single-ended or differential probe. Okay, so the 1-to-1 passive probe basically is just a coax. I'll show you a schematic here in a moment. It actually has significant input capacitance, and that is undesirable. The input resistance is kind of low. Typically, a scope is 1 mega ohm, and this very simple probe actually simply passes on the scope input resistance to your device under test. And the input range is whatever your scope is limited to, so I cannot use the 1-to-1 passive probe to extend the input range. And it's good to about 10 megahertz, or at DC. Many measurements are done at even lower frequencies. Once I get above about 10 megahertz, as a rule of thumb, or about 1 megahertz, I'm going to differentiate here too between bandwidth and what my typical measurements are. So in the case of the 1-to-1 passive probe, the bandwidth might be 10 megahertz, but I may only use it up to about 1 megahertz. Because remember, at 10 megahertz, it's 3 dB down. That's a 30% error. And I generally kind of use a rule of thumb, divide that by 3. So 10 divided by 3 would be about 3 megahertz. And I would actually recommend using that at even lower frequencies because of some other issues such as the input capacitance. The 10-to-1 passive probe has a resistor network that bumps it up to 10 mega ohms input resistance at the tip. It has much lower input capacitance, which is desirable. It extends the voltage range of the scope. It has a minus 3 dB of around 500 megahertz typically. And again, I would not want to use it there. That's a 30% error. I would use that, just say a rule of thumb, divide that by 3. And that's about 160 megahertz or somewhere in there, 166 megahertz. But typically, because of some other issues that it has, this input capacitance, I'm not going to recommend that you use it above 50 megahertz. And you'll hear me repeat this a couple of times during this seminar. The 100-to-1 passive probe has a higher input resistance, modest input capacitance. It can extend the range to 4,000 volts. We offer one that goes to 30,000 volts. The bandwidth on it is reduced, but still 100 megahertz is pretty good for such a simple passive probe design. And it's a single-ended measurement, so you reference your measurement to ground, and it is for high voltage measurements. Similarly, a 1,000-to-1 probe, it has similar bandwidth, similar use, and it would go to 20 kilovolts. And a 50 ohm low capacitance probe. This is a very, very specialized probe. I'm going to show you a schematic of it. It has a very low input resistance, so you really want to watch that. It has an extremely low input capacitance. That's a very good thing. And as a result, it can go to very high bandwidth. We sell one that goes to around 6 gigahertz or higher if you take precautions with it. This is for high-speed measurements. And when I say high-speed measurements, I don't really mean high-frequency measurements, but I may mean signals or waveforms that have high-frequency components in them. And that is indicated by any waveform that has a very fast rise time. So we're talking about square waves there. A FET probe, this is an active probe. It's a single-ended probe. Most engineers just call it a FET probe because it has a FET in the front end. And it has unique characteristics. Typically, its frequency range is around to 1 gigahertz. If I take that same design and I put a BJT, bipolar junction transistor, that's very often called an active probe. And that extends the frequency range up even higher. And then we get into differential probes. That's a probe with 2 leads in it. And differential does not mean isolated measurements. At a glance, you may feel that it does, but differential is not isolated. They're not the same thing. But a differential measurement would be any measurement that I take between 2 points and neither point is ground. So sometimes we call that a floating measurement. Okay, and then there are another category of differential probes, higher speed differential probes. So that's a classification. Okay, so let's take a step back to the very first row on that chart that we just discussed, and we're going to talk about this very simple one-to-one passive probe. So a one-to-one passive probe really is just a piece of coax. At the end that connects to the scope, it may have a little BNC box. There's no adjustments on it. It's really often just a BNC connector. I've modeled as a lump element this 50 to 80 picofarad cable capacitance, and that's just the capacitance of this coax. This coax could be, it could have intrinsic impedance of, say, 50 ohms, and it very commonly would. But because it's not terminated properly at either end, really what it looks like is just a big capacitor to your test point. And so that's the biggest drawback with it. Looking into this probe assembly, the tip here, my device under test would see a somewhat heavy capacitor and a modest or low input resistance, 1 mega ohm, not too low. Actually, it would see around 100 picofarads because I'm adding 80 picofarads of the capacitance to the 20 picofarads of the scope, which is very typical. And 100 picofarads is not going to be a problem to about 1 megahertz. So you may glance at this probe and it may see 10 megahertz on the side of it. I don't want you to use it at 10 megahertz. You'll have a 30% error. If you're looking at sine waves, maybe it's fine, and you can just get an idea of what your waveform looks like, and that may be sufficient. But if you want an accurate measurement for a passive probe, divide what is marked on the probe, divide it by about 3. So 10 divided by 3 would give you about 3 megahertz. And just to play it safe, I wouldn't use this much past 1 megahertz. Okay, and then here's another rule of thumb too here. If you really want to be out of the woods with any kind of error, go for about 10 times. So this is a good example of that. This is probably a 10 megahertz design, 3 dB, in 3 dB terms, 30% terms, but I would use it to 1 megahertz, which is a factor of 10. Okay, so a 10 to 1 passive probe has a little bit more to it. It has the same piece of coax, but what we've done is we've come in here and we've put in a 9 mega ohm resistor, and that works against the 1 mega ohm resistor in the scope to form a 10 to 1 voltage divider. In parallel or superimposed right on top of that very simplified schematic of resistive divider, we have a capacitive divider. So we have 10 picofarads here, and then all of these capacitors here combined with an adjustable one forms a AC divider. And so any AC waveform is going to be divided also by 10 to 1. So basically, from DC all the way through AC and up to 500 megahertz, which is what you'll see marked on this probe typically, your waveform will be divided by at least 10. As you approach the 3 dB frequency, it's going to be significantly further down. So this is a 10 to 1 probe. Basically, there's an adjustment on your scope that accounts for this and allows you to read directly off the scope without having to do any math in your head with this divider. So this probe might be useful to around 50 megahertz. At 50 megahertz, it would have very little attenuation, so very little error, and you could expect very accurate shapes or waveform fidelity of your measurements as well as amplitude. And again, you can stick with the 10 to 1 rule. If you have to, you can cheat a little, and you can kind of do a 5 to 1 ratio. You could use this probe a little bit higher. I wouldn't go past 100 megahertz with it in a pinch. At 50 megahertz, you'll want to consider an active probe, and we'll talk about that here in a few minutes. So on the front of all scopes, you'll see a pair of pins. One is ground, and one is a 1 kilohertz square wave. This 1 kilohertz square wave has some reasonably fast rising edges and falling edges, and that means it contains a good deal of high frequency components. If we adjust the compensation capacitor on the scope and we get a nice square wave like you see in the first picture here called labeled as correctly adjusted, then we can be assured that this probe has been phase compensated or equalized, and that basically all of your AC components, all of the harmonic components will be attenuated at the same ratio. And in this case, we wanted a 10 to 1 attenuation ratio. So that's the adjustment of the capacitive voltage divider. Once you adjust the square wave adjustment on any given channel, we leave that probe on that channel. If you move it, you'll need to recompensate it. Okay. So what happens with passive probes at higher frequencies? Okay. Basically, the coax will begin to resonate. In these designs, the coaxial cable, I've indicated, would be probably 50 ohms, but it's not terminated into 50 ohms. So it will resonate. It will have a standing wave on it, which means it will not transfer the waveform properly. The amplitude of it would be canceled due to reflections that are occurring on this approximately 1 meter long transmission line, or maybe 3 meters. Most probes are around 1 or 1.5 meters, and the resonant frequency of that is around 50 megahertz. So you don't want to go above that. And I'm going to show you some real-world schematics of these passive probes here in a moment. But I want you to understand that that coaxial cable in there has been intentionally selected to be very lossy. And it's lossy on purpose. It has resistive elements in series with the center conductor. The center conductor is around the diameter of a human hair. It's very thin. You need to handle these probes with care. And the series DC resistance of that center conductor is 150 ohms for a 1 meter length of it. Now, if you have an old probe laying around and you measure it, and you don't find that lossy resistive element is in there, that's probably a low-cost probe. Maybe it's a generic probe, or certainly it's a low-frequency probe. Okay, so those series resistors are there intentionally, not to terminate the transmission line. You'll see us do that later in a design, but it's there simply to damp the reflections. In other words, we don't really mind if the reflections or the resonance occurs, but we need to damp those and keep them to a minimum and keep them out of the scope. Okay, so what does a real 10 to 1 passive probe look like? If I took one of these apart, and I have, you'll find that they're not as simple as the first schematic that I showed you. Certainly the capacitive divider is there, and the resistive divider is there, and there's always at least one adjustable capacitor. In practice, there's usually more than one. But in addition, in the BNC box or the probe head, you may find some other adjustments like damping resistors that are adjustable, or maybe another damping resistor that's in series with the adjustable phase compensation capacitor. And here I've modeled the series resistance of the lossy coaxial cable. Inside of the scope, we continue with more of the same design. Damping resistors to cancel or dampen the inductance of the input preamplifier board there, or attenuator board, and series resistors with the other elements as well. So if you have an old 10-to-1 probe and, you know, maybe it's damaged or it's ready to be discarded, take it apart before you do and see what's in there. Okay. So I get this question regularly. If I use brand X probe with the Yokogawa scope, what could go wrong? What happens is maybe the probe is matched to another piece of equipment, or maybe it doesn't even have any of those efforts to manage the reflections or the resonance. And so I've intentionally set up an experiment here. On the right, I used the wrong probe with one of the Yokogawa scopes, and I gave it a square wave. And what it did was the square wave has a lot of high frequency energy in it, in the rising edge of it, and it excites all of those LC components, and you can see here that it rings. And I'll show you the equation here for that ringing frequency, but it's a series LC circuit, and it stores energy, and it releases that energy, and what you end up with is a little sine wave on your rising or your falling edge of a step input. If I use the right probe, it has all of the efforts, the damping resistors, and the lossy coaxial cable, so it manages that ringing. You might see just a little bit of ringing on the step there, and that's often unavoidable. But certainly I can still get a good measurement out of that. With the wrong probe, I'm left to wonder, is that my device under test that has that waveform, or is my scope doing that to me? So if you see that, be suspicious. Make sure you have the right probe. And then the next thing you'll want to look at is your ground lead connections. And I'll give you examples of that in a moment too. Okay, here's a very specialized probe that's called a low capacitance passive probe. If you Google this, you'll see that it's called a Z0 or transmission line probe. And if you have these items around, you can build one as an experiment. We happen to make a very, very high quality low capacitance passive probe using very good components here. And these are components that have minimum parasitics in them, so that my resistor really looks like a resistor even at 6 gigahertz. And similarly with the termination resistor in the scope too. So how does this work? Okay, in this case, it's a transmission line that is in fact properly terminated at the scope end. That means if we propagate a waveform from the device under test through the probe head, which is a resistor, through the coax, it's not going to resonate, it's not going to ring, and it's not going to bounce or reflect back and create standing waves. No, it's going to properly terminate and dissipate. And the scope now has a nice clean waveform there to measure with no reflections and no ringing. So it's a low-cost probe, really. It's 3 parts, coax and the input resistor. You may wonder why I don't have a 50-ohm resistor at the probe head. Well, I'm not propagating a waveform in that direction, so I really don't care if that is properly terminated. All of my waveforms propagated to the right on this page towards the scope and were absorbed and dissipated by the resistor, and none or minimal, almost none, bounced back, and so we didn't have to worry about terminating that far end. And it also gives us, I think, about a 20-to-1 voltage ratio here. You can bump the 450-ohm resistor to about 900 ohms and have I think it's about a 50-to-1 voltage ratio. You can put a series input capacitor here and block DC. But as you can see, it's a very specialized probe. I spent some time on it here for you too, because it's actually a really neat, simple design, and it's been around a very long time. you can learn a lot by examining how this works, and it helps you to begin to understand how the other probes, the 10-to-1 and the 1-to-1, work or don't work in some cases as well. Okay, so here's an active probe. What is in an active probe? Most of what goes into an active probe goes into the probe head, and that's for a reason. We put an amplifier or a buffer and a resistive capacitive divider network in there so that we can avoid all the problems that this coax causes. And we drive the coax properly with a low impedance source. Again, it doesn't need to be a 50 ohm impedance. It can simply be 0 ohms or 1 ohms. And we can drive this coaxial cable line without any ringing or any of the monkey business that we often see in the passive probes. And in the far end, it's properly terminated, and the scope gets a nice, clean, high-fidelity waveform for you to perform measurements on. This is generally a low-input capacitance, and you'll hear terminology, sometimes FET probe, and that has a very high input resistance. Or you'll hear someone say active probe. That could still be a FET probe, but usually that means bipolar probe. So that may have a higher bandwidth. And some other trade-offs with the input resistance. So these are specs that you want to look at when you consider an active probe. Okay, here's a differential active probe. It looks pretty simple. It looks like just two active probes or a resistive divider tied into a diff amp. And that's what it is on the schematic. But more importantly than that, this front end here, these resistive and capacitive dividers, these are certainly, high performance, low parasitic components. But more than that, they're laser trimmed, and usually there's an adjustable capacitor in here that's very stable and can be adjusted. These have to be matched exactly to one another to create what is called common mode rejection. So that's one of the specs of a differential active probe is common mode rejection, and that specification is called common mode rejection ratio. So if I tie the positive input and the minus input together, and I apply a voltage to those, this diff probe should not measure that and display it on the scope. It should still display 0 volts here. And similarly, if I tie these inputs together and put a sine wave there, very, very little of that should leak through here. So that allows you to make a very clean measurement with minimum noise from 2 points, neither of which is ground. Now, you can use a differential active probe to make single-ended measurements, and there's at least a few cases where you would want to do that. It has some advantages, especially if you measure switch mode power supplies. The minus input here can be tied to ground, and there's a very high impedance path here, so virtually no path for ground currents or ground loops to occur. So again, you get cleaner measurements using a differential active probe in a single-ended manner. And so these are also used for serial communications or logic. We market some that are designed to work in the range of 20 volts, and we market some differential probes that are rated for around 7 kilovolts as well. And notice that my differential amplifier here does not have any symbol for isolation. There's no galvanic isolation here. So this is not an isolated probe, nor is it an isolated amplifier. And isolation usually is something that you consider when you need to keep your measurements from affecting one another, and also in terms of safety. Okay. We've actually touched on each of these probing problems, one of which is loading effects. Your probe always loads your device under test at DC, at AC, and it loads it more and more so with increasing frequency. I'll give an example of that. Your probe is a filter. It generally is a low-pass filter, and we would hope that it's a very high frequency cutoff, and but we need to pay attention to that. Putting a probe into a circuit creates another filter too, and I'll show you an example of that. It's an inadvertent filter that's formed by the probe's input capacitance. and resonance. We've talked about that in the passive probe coaxial segment, but I'm going to show you an example of resonance caused by the probe on your device under test, and specifically with the ground lead inductance. And then we'll talk about stability of the ground level. Okay, so here's a schematic, and we have a device under test here, and I've got a measuring instrument here that has an input resistance and capacitor model. You might think of this as the front end of a scope or the front end of a probe. And when I tied this network into my device under test, the device under test has a source impedance Z sub S, and this is the equivalent circuit of that device under test. Obviously, I've formed a voltage divider right there. So this is why you want to consider your device under test impedance. If it's a low impedance and you know it, you're ready to go. If you don't know it, you need to figure it out. There's actually a way to measure it. Sometimes you can just look up a spec, and then you'll have some notion of, how significant these components are against that source impedance as a voltage divider. So you can take these three components and calculate roughly how much loading that you're creating, both at frequency and at DC. So to reduce load effect, choose a probe with high input impedance, and keep an eye on both the input resistance and the input capacitance. Okay, here's a comparison of three probes. The red graph is a low-cost passive probe, and with increasing frequency, it actually has decreasing input impedance. So at 100 megahertz, it's a 113 ohm impedance. Most of us don't want to put a 113 ohm impedance on our test point. Some test points may tolerate that, but most will not. So let's go back down to where I recommended we stop using it, or in the case of the 10-to-1, that's around 50 megahertz. So somewhere right in there. It's still not quite 1,000 ohms, and 1,000 ohms is certainly a lot better. You can make measurements with that. The next probe here is it's green, color-coded. It's an active probe, not necessarily that low cost. It starts out with a somewhat much lower input resistance, but a very, very small input capacitance. And as a result, it's much better behaved. In fact, it's flat, almost up to a megahertz, and then certainly very useful if we cut it off at a kilo ohm. We could use it to well over 100 megahertz and beyond with some other precautions as well. Okay, and then here's the Z0, the low capacitance probe that I told you about. This is the transmission line probe, and we have this one set up for 500 ohms. These can also be set up for 900 ohms. So this one starts out at 500 ohms, pretty much stays there all the way up to several gigahertz. So obviously your circuit has to tolerate 500 ohms. But what it does best is its ultra low capacitance, and that's what extends the frequency range on it. Okay, so I told you the probe was a filter. Well, when I connect it to any device under test that has a non-zero source impedance, I've created another filter, and that is this is half of the divider here, or the Thevenin's equivalent of these two resistors. So in any event, you've got a source impedance, a series source impedance at your device under test, and then you're shunting to ground that test point with a resistor and a capacitor. So there's your filter, and I quickly have calculated using the known specs for one of our passive probes, a 10-to-1 passive probe. It has 14 picofarads of input capacitance, and so it has a minus 3 dB low-pass Gaussian effect on your test point of 455 megahertz. So that could be an issue with seeing some of your high-frequency components. And certainly the active probe would do a lot better. It has a very, very small input capacitance, so that it has a cutoff up at 7 gigahertz. Okay. Here we've got resonance caused by inductance. When I insert this passive probe here, I create an equivalent circuit here, which is a series LC circuit to ground. So the input of the probe is the capacitance to ground, which is in series with this ground lead, and that's an inductor to ground. So there you go. It's C and then L. And there's a resistor in there as well. So that resistor would tend to damp any kind of ringing that might be caused. But let's suppose that the output of this input buffer has a rising or a step function output, just a fast rising edge on it. It's going to excite or to give energy to this LC circuit, and hopefully it will damp. And you'll see here an example where it does not damp. Okay, so I took a passive probe and connected it to exactly this type of circuit. I gave this scope and this passive probe with a very long ground lead, a step input, and certainly I get significant ringing. And I'm left to wonder, is that my device under test doing that? Do I have a problem? Or is that my probe? So as it turns out, it's the probe. What we did in this example here was we shortened that ground lead by using a little ground pin. And there's more than one way to do this. We sell accessories that make this pretty easy. You can solder little pieces of wire to your circuit board or your device under test. And no matter how you do it, keep your ground lead very short whenever you're dealing with fast rising edges. Okay, so that's an example of the scope probe is a resonant circuit, and here's a equivalent circuit of it. We've got a step function in our device under test, and it has a source impedance. And then here's the rest of these components here, the C and the R and the L. It's a series LC circuit. That's our probe, which I just demonstrated to you. And if we know these components, and they're generally pretty easy to figure out, a length of wire is just a few nanohenries, around 10 nanohenries per centimeter. So a length of wire would be 150 nanohenries. And if you punch those into this equation, you'll see that the ringing frequency for this LC circuit would be easily calculated, and I've done it here for 3 different setups. So for the PB500, I might have a resonant frequency as low as 100 megahertz when using the long ground lead. So that's going to be a problem. I don't have to get to 109 megahertz with this probe to excite that LC circuit. I could excite it with any fast rising edge. So in this case, I could have a 1 megahertz waveform with a very fast rising edge, and it will offend this LC circuit. It'll energize it, and you'll get ringing. So that's very easy to hit. It's very easy to excite a passive probe with a fast rising edge. It would be a little more difficult with the 2.5 gigahertz active probe, but you would still want to keep the ground leads on it short. You'll probably be making high frequency or fast measurements with a probe as sophisticated as this, so there's still a chance you'll excite it as well. So if you see ringing edges, think to yourself, I've got a long ground lead, and you'll need to deal with that. It is possible too to get similar effects with any scope where you're using the display interpolation in sine x over x mode. You'll want to turn that off if you're measuring fast rising edges. And just turn that off or turn it to a line or a pulse type of display interpolation. Okay, so here's some hints for high frequency probing. Keep your leads short. Reduce the input capacitance. Here's an accessory that we sell that allows a low-cost passive probe to be connected very easily to a trace on the board. And actually this thing can solder on, and it's a little spring. It'll actually hold the probe in place, so that'll leave your hands free. We sell some devices for our active probe that would be soldered directly. In this case, the ground inductance would be kept very small, and the lead there would be kept very, very short. function, and the resistors have an advantage of further dampening any sort of ringing. And I'll give you an example of that here too in a moment. Okay, so I mentioned the damping resistor, and to the left here we have our device under test, which intentionally we've chosen a step function that has a source impedance that we may or may not know. And then this LCR circuit here, this LC circuit, is our probe. We've demonstrated that that can be excited and create the ringing. So what we're going to do is put in series with it a damping resistor. This damping resistor will be chosen small enough that it is not going to affect the amplitude of your measurement. So as long as you've kept an eye on the source impedance and that you know that this probe is appropriate for the measurement in the first place, you can go to several hundred ohms easily, and this won't add any appreciable attenuation. So what value of R do we use? You'll see a couple of typical values here. If you wanted to go through the math and you wanted to set Q, which is quality or damping factor, to 0.8 is a really good number to start with, then you can crunch these equations here using the values of the components that we know are in our probe, and then you can solve it for R sub damp. Typically, if you do that, you'll end up with a value of 220, 240 ohms, somewhere in there. Just choose the nearest value off the shelf. And you can see that these damping resistors actually make your measurements a little bit easier. They give you longer leads, which is exactly what I've been telling you not to do. But sometimes you need longer leads. And in fact, in this measurement, I've used the damping resistor plus some little segments of wire. And this keeps the stress off of the test engineer, but certainly off of the probe as well. So the probe there is laying casually and taking this measurement. And so without the damping resistor, this test setup I had here, I found that I was very easily able to excite certainly these very long leads I put on it. And I got just a fantastic ringing on that rising edge there. And then I put in the 220 ohm resistor, same scope, same probe, and in this case I've got a really nice, clean, square rising edge that I can make solid measurements on. And it gives me the assurance too that my device under test does not have ringing in it on its own accord. Okay, so let's do a quick summary of the passive probes that we've discussed here. Passive probes are suitable for low frequency signals. As you've seen, they're suitable for frequencies lower than what is marked on them. In other words, they're 3 dB frequency. If you really want to be in the clear on that, divide that number by about 3 and stay below that number. So we saw that a 1-to-1 probe, which hopefully you won't use much, but if you have to because you have very small signals, use it to about 1 megahertz. A 10-to-1 probe is good to about 50 megahertz. Okay. The compensation adjustment is basically the equalizer for flat frequency response. And so that's important too. It keeps the shape of your waveform. You saw how distorted a square wave could become with a misadjusted compensation capacitor. Use the shortest ground lead possible. I hope that's still fresh on your mind. We saw about 6 slides of how easy it is to have, even at low frequencies, you can have a probe to ring due to the LC circuit that is part of its makeup. And the issue there is the fast rise time of your waveform. The input capacitance results in a loading effect. And here's a quick example. The 10-to-1 probe has around 14 picofarads of capacitance. At 100 megahertz, this impedance is only 113 ohms. So we saw that on the chart. And I'm sure none of us want to connect a probe that's got 113 ohms of loading on it. So stay at lower than the rating. Stay at 50 megahertz or less. And this surprises many engineers. They've got a 500 megahertz probe, and I'm telling you, don't use it above about 50. So it's a good lesson for any kind of passive probe. Passive probes tend to have a rather heavy loading effect, and you saw several examples of that. Okay, so for high frequency measurements, just try to remember anything above 50 megahertz, you need to consider an active probe. And most of these active probes, these are in the $500 to $1,000 range. Certainly you can spend more as you get into higher frequencies, but an active probe or a differential probe really doesn't have to be that expensive, maybe several $100s. I know we've got some in that price range as well. And these can extend your voltage range too. We've got these in 10 to 1 and 100 to 1 and 1,000 to 1 attenuation ratios. The low input capacitance of an active probe results in a much higher resonant frequency. That means you're less likely to get ringing. You're less likely to excite it with a step function or a fast rise time. Even so, keep your ground connections short whenever possible. And if you see ringing, learn to recognize it and to know the cause. Okay, we're going to talk about current probes. I've got just a few slides on this. We're going to start with a very simple AC only current probe. These are often called CTs, or current transformers. And it's called that because it is in fact a transformer. It has a single turn, and when I say turn, you see that this actually doesn't turn or go around the core. A turn in the transformer world is one pass. If you pass through the core one time, that's one turn. So this is a one turn to many turn transformer. That means I take this current here and I create a current here according to the equations that govern transformers, and I terminate it into a resistor. So I have that current into that resistor, and I can now measure the voltage across that. And that voltage follows the input current linearly. So here's a schematic form of exactly what we just discussed, an AC current probe. These are low cost. As you can see, it's just a ferrite and maybe a box with some connectors on it. Some of these articulate. You see here one that can, the core can actually open itself up, a pair of jaws there, and be clipped on. This has banana jacks on it. It's designed for a DMM, or digital multimeter. Many of these can still be used with scopes. You just need an adapter, and you need to make sure that you use a voltage output type device, and that's what this is. This has voltage out, not a current output. Okay, so what if we want to measure DC? Okay, we got a trick up our sleeve for that. It's the same transformer, the same core, but we come in here and we cut a slit in it. We put a Hall effect sensor in there, and that gives us the DC because it produces a DC voltage whenever a DC flux is passing through it. That DC is fed to an amplifier, which as a first step, it actually goes back and creates an opposite canceling DC flux in the core. So we keep the core at a bias point of 0, and it stays neutral. It cannot be saturated. So it's a very clever function of this first amplifier and this feedback core. But also we pass that signal on to be conditioned or buffered and then added back into the output. So now we have an indication of how much DC current is passing through our device under test, this line here. Similarly, we have a little buffer amplifier that picks up on this winding here, and that represents the AC waveform. We've added the DC measurement and the AC measurement together, so we have an AC plus DC measurement, and that's an AC-DC current probe. These cost significantly more. They're sensitive, certainly to any sort of abuse, any kind of heat, and being dropped. So these have to be treated with great care. Okay, a current probe doesn't even have to touch your circuit, but it actually does have a loading effect. And in the case of a current source, we are actually introducing a insertion impedance, so a series inductor. So just imagine that you are breaking your circuit here and adding a series inductor. And also, as a function of the vicinity of the clamp around your wire, there's a very small parasitic shunt capacitance to ground. So you see you have a second order LC low pass here. So you have to watch that. So you need to know the source impedance of the current source that you're measuring. And here's a loading effect of one of our probes. So this is one of the specs that you want to look at, and then you want to consider the source impedance of your device under test as well. Okay. One of the specs for current probes is bandwidth. You want to look at what's the largest conductor one of these articulating clamps can adapt to, or the jaws can fit around. And we've got some very small ones and some very large ones. Certainly, you're going to look at how many amps they can measure safely. What is the range on it? What is the absolute max peak? You'll see one spec, too, that's called amp seconds. And it won't always be specified very clearly, but it will say something like, this probe can tolerate 1,000 amps for 30 milliseconds. What you do there is you multiply 1,000 amps times 30 milliseconds, and you come up with the amp second rating. So you can consider that in terms of your application. You have to think to yourself, will I ever exceed that? If you do, if the answer is yes, you need to select a different probe. Exceeding this will permanently magnetize or damage or heat your core. And sometimes they'll make the same specification with reference to a duty cycle. So you have to pay attention to that too. And then, of course, just like a voltage probe, they'll specify, except it'll be current, they'll specify a maximum peak current or a maximum RMS current. So you generally don't want to exceed those, although the probes are designed so that you can occasionally exceed it. And it'll usually have that pretty clearly spelled out for you. Okay, if you start making power supply measurements, or if you are ever making voltage and current measurements simultaneously, you'll be interested in skew. And skew is the propagation delay difference between the two waveforms. So this voltage waveform propagating along this simple passive probe arrives at the scope very quickly, but arriving probably on the order of a few nanoseconds behind it will be your current waveform. After all, it's going through some magnetics, a buffer amplifier, possibly a different a coax with a different propagation delay spec on it. And if they arrive at different times, your waveforms actually will be slightly out of phase with one another or skewed. We call that skew. Almost all of our scopes have an automatic D-skew, and to work it, you simply connect the current probe and the voltage probe to this current loop on this D-skew signal source and this voltage source here. This is a 15 kilohertz step function. Those will be displayed on your scope. You push a button, one button D-skew, the scope will find those two waveforms. It will insert a correcting delay into the voltage line. You can also do it manually. You can do this with a manual adjustment. Our scope will permit that. But this certainly makes it a lot easier, and it's fairly low cost. So you might think, well, a few nanoseconds can't hurt anything. And it's true, probably many measurements, that won't matter to you. But I can tell you with switch mode power supplies, 5 nanoseconds on a fast rise time switch mode power supply, like a buck converter, 5 nanoseconds can probably add around 5% error on top of whatever other error you already have. So it's very worthwhile. Common mode noise. Here's a little trick for using 2 current probes. If you're lucky enough to have 2 of the same or similar current probes. Oh wait, no, this is not the right demo. This is common mode noise. Basically, what I'm stating here is that you want to use your current probe not only for safety, but also for noise on the lowest voltage side of your load. If you've got a circuit that's anything similar to this, you want to stay on the ground side. And less of the voltage will couple through that straight capacitance into your measurement. Okay, and here's a trick for rejecting external noise. If you have 2 of the same or very similar probes, you can lay one down alongside of your measuring probe and pick up that noise intentionally, and then go into the scope and subtract that noise on channel 2 from that measurement plus noise on channel 1, and you'll end up with a little bit cleaner measurement. You can adjust the amount of noise that's coupling by adjusting the little slider here, the articulating jaw. Just open or close the jaw very slightly, and that will let you modulate the amount of external noise influence into your measurement. And here's another tip. Many of you are aware of this already. You can pass your conductor through your core of your current probe several times. Each time you do it, it will add one insertion impedance to your device under test, so be aware of that. Usually passing it through there one or two times is sufficient. Beyond passing it through there several times, it would be time to select another probe, one with a lower range, better sensitivity. So in other words, you may not want to use a 100 amp probe to measure 1 amp. At 1 amp, I would say get a 10 amp probe. And this is a fairly common thing to do too. You'll use your linear scaling function in the scope so that it accounts for the gain factor here that you've produced. Okay, so the 4 waveforms that I showed at the very beginning of the presentation, the correct waveform, the best waveform fidelity measurement that I was able to accomplish there was waveform number 4 of 4, and a quick review of that will reveal why. So my waveform was a square wave. It was at 200 megahertz. It has very fast rising edges, and I measured it with a passive probe with a long ground lead. And in this case, at a glance you might think, well, that long ground lead would create ringing. It didn't even have a chance. The input capacitance at 200 megahertz had loaded this waveform down so much, it was basically being filtered and loaded simultaneously, that the square wave was lucky to look anything like what it did, which is almost triangular, sort of a sine wave. And in the second measurement, I took that same probe and shortened the ground lead. So that was another attempt to measure it. Looks a little bit more like a sine wave. So clearly a square wave would have many, many harmonics in it. I would say in this case just the first 3 components of that series is making it to the scope. Okay. The third measurement, using a really nice 2.5 gigahertz active probe, produced a much better, almost square wave of that little 200 megahertz square wave. And that's on a demo board that we have connected there. So finally, I've connected a series damping resistor. And the 50 ohm terminator here really plays no role in this measurement. It's just an easier way to connect. But this damping resistor created what certainly nearly resembles a square wave. And at this point, I can see that my waveform, which is a square wave, has some problems of its own. The board that it's laid out on creates its own reflections, or the output amplifier that's producing this waveform has problems. So there is, here's my contact information. This is about 3 hours worth of material that I fit into an hour here, and I'm certain that you have questions, and I would love to hear from you, find out about your application, see if there's any way I can help with any probing questions that you have. And if you have colleagues that are curious about probing too, I do this seminar several times a year. So get in touch with us and let us know that you have colleagues that are interested, and we'll help them get signed up to see this probing seminar in the future.
Thank you, Barry, for a wonderful presentation. We have run out of time for our Q&A section. Please be assured that if you submitted questions, they will be answered via email. Also, if you have not yet answered the poll questions, I would request you to please do so at this time. I'd like to mention that the seminar was recorded and will be available for replaying in archive form 24 to 48 hours under the technical library of our webpage. I'll be sending everyone a link when it is put up for your viewing. Thank you once again, and we hope to see you online at our future web seminars.